Hey, fellow mathers! Before we get into this episode, we want to share with you how you can get access to free content, professional learning that will keep your students engaged and doing the math that matters. Get ready to go to this link, mathisfigureoutable.com/challenge.
That's right. Registration is open for the free Math is Figureoutable Challenge that's starting May 15th and runs to the 17th at 7 p.m. Central. We're going to have 3 nights jam-packed with learning and routines that you can take straight to your classroom.
In these challenges, we have a great time. We do some math, talk about classroom experiences, give away super cool bonuses and prizes. You won't just walk away with routines that are naturally engaging and encourage your students to think mathematically. You'll also have a chance to win over $6,000 worth in prizes, including a few virtual PD sessions for your school. I'll be joined by my wonderful co-host Kim and special guest Jenna Labe.
You can register at mathisfigureoutable.com/challenge for a fantastic learning experience. That's mathisfigureoutable.com/challenge. Now on to the show.
Hey, fellow mathematicians! Welcome to the podcast where math is figure-outable. I'm Pam.
And I'm Kim.
And we make the case that mathematizing is not about mimicking steps or rote memorizing facts, but it's about thinking and reasoning, about creating and using mental relationships. We take the strong stance that not only are algorithms not particularly helpful in teaching, but that mimicking algorithms actually keeps students from being the mathematicians they can be. We answer the question, if not algorithms and step-by-step procedures, then what?
So you know already that we love problem strings as a really cool routine. And if you were listening last week, you heard us talk about another great routine called As Close as It Gets.
Yep.
There are others that we love so much.
Nice. Now, they're not like an infinite number of others. Like there's a few that we really like. And some of them are kind of the ones that we've put our particular bent on, our sort of magic touch to. But we definitely like this one, relational thinking. And I'll give the CGI group credit for putting it in their algebraic thinking book where they talked about the meaning of the equal sign and got me really thinking about relational thinking problems. And now I use them a lot. And so, Kim, you get to be on the hot seat. I'm going to ask you some questions. The point of relational thinking is that you give students an equation and there's a blank in the equation. And when you give them the equation, so Kim, when I give you this equation today, I do not want you to do a lot of computation. I for sure don't want you to use equation solving strategies. I really want you to use relationships among the numbers to reason about the number that's missing. Okay?
Okay. Yep.
All right. So the first one, 15 times 18 equals 30 times blank. Let me repeat that. 15 times 18 equals 30 times blank. All right.
Okay. All right. So I'm thinking that I have twice as many of some things. So 15, twice as many of them would be 30. So then I need half as many as the size of the things. And I don't know that I said that so well. I'm going to let you clean up my language. And I'm going to call this 30 times 9. Because if I have twice as many, 30, then the size of those things can only be half as big. So 9.
So we could use groups here. If I have 15 groups of 18.
Yep.
But I'm telling you that's equivalent to twice as many groups.
Yep.
What would have to be the size of the group to have the same number of things?
Yep.
That's a way to say that. Another way to say that you and I were both really general. Another way to say that could be if I have 15 18s, I'm going to need 30 9s to have as much as I want. If I have 15 18s, I'm going to need, and I have twice as many, I can't say twice as many 18s, but I'd need twice as many groups that are half as big.
Yep.
Okay, cool. So you're filling the blank with 9. All right, nice, okay. Nice. Okay, cool. Next one. 6.1 or 6 1/10 minus 2.9 or 2 9/10 equals blank minus 3. 6.1 minus 2.9 equals blank minus 3.
Okay. Oh, so I've thought about this before. So here's what I'm thinking. I think not about this particular problem, but I know that if I'm going to take away, I want to take away something nicer. So I think about the actual distance between 6.1 and 2.9 on a number line.
Totally just drew that on my paper.
Yep, me too. So if I think about the gap between those two numbers, I don't really like those. I'm going to actually shift that slightly to the left, like 1/10
To
to
the
the
left
left.
or to the right?
Oh, I wrote it like 6.1 minus 2.9. So if I put it on an actual number line, then I'm going to shift it to the right.
Okay.
I have the problem written down on my paper.
Gotcha.
So that's going to be 6.2 minus 3, because the gap between 6.2 minus 3 is the same distance as the gap between 6.1 and 2.9.
Nice. Yeah, so I just wrote on my paper 2.9 on an open number line, and then off to the right, I wrote 6.1. And then I thought about the relationship between that 2.9 and the 3, and that 3's to the right of 2.9. So I knew if I was going to shift that distance up just that 10th, then it would shift 6.1 up. Let's say sort of that jump. I kind of have a jump drawn between 2.9 and 6.1, and then I shifted that jump up to 3 and 6.2. And that looks just like, okay, sorry, I had to say out loud what I'd written on my paper. Cool. All right, bring it. Here's the next one. What about 3,999 plus blank equals 4,000 plus 2,587?
Okay.
So 3,999 plus blank plus what equals 4,000 plus 2,587?
Okay, so I'm actually looking at the difference between 3,999 and 4,000.
Okay.
And so I'm thinking about moving marbles, actually.
Okay.
And I'm thinking about if the right side equation, this right side of the equation, the 4,000 part, that amount I want to be equivalent to the amount on the left side of the equation, right? That's what the equal sign means. And so I'm going to have 2,500. I'm so distracted. I'm so sorry.
It's raining.
I know.
Just so y'all know,
it's thundering.
We're recording on
I'm sitting by large windows.
Very rainy, gray, overcast, loud thunder, lightning.
Oh my goodness.
Fun recording day.
Okay. So I'm
Kim,
thinking,
do you need time or help?
No, I don't need, I actually didn't need either at this moment. I wrote something down. Okay. So what did I just write down? 2586, sorry, is what I wrote down.
You think it might be 2586 because?
Because I have, did I write the number down? Say the numbers to me again.
3,999 plus blank equals 4,000 plus 2,587.
Oh, I wrote the wrong number. Say it to me one more time. 3,000. This should not be this hard.
3,999 plus what equals 4,000 plus 2,587.
I wrote the number down wrong. Okay, 2,588.
Why?
Because I have one more marble in the pile I'm looking at the right side of the equation, the 4,000, and it's as if I moved one marble to the right from the 3,999 to the 4,000.
Okay.
So I'm going to move one marble.
You're not liking this one, are you?
No, I'm not. Why am I so distracted? Okay, I'm thinking. I know that it's 2588. I'm having a hard time verbalizing.
I mean, and that's huge, right? That's like a real thing. That's like a for sure thing. Once you have that 2,588 written down and you look at the 3,999 plus that 2,588, what would you do?
Oh, because I'm trying to move marbles across the equations. I want to move a marble from the 2588 to the 3,999 to make it 4,000 plus 2588.
Plus 87.
87.
This is the devil problem for you. Kim is not liking this problem. Cool.
Oh my goodness gracious.
Well, so that's interesting because for the moment, you just sort of got caught up a little bit in moving marbles across the equal sign.
Yes, I did.
But that's not sort of helpful if you're really just trying to solve the problem. 3,999 plus 2,588. If that's the problem you're trying to solve, then you're really just moving marbles between those two numbers.
And all these listeners right now are screaming, saying, this is what it is. And I love that you asked me, do I need time or help? Right? That because yelling numbers at me, clearly I'm not writing them down right when you say the first time. So yelling numbers at me wouldn't have been helpful. Oh my
Cool.
goodness. All right.
So at the risk of you like being done, can I give you one more?
Sure, absolutely. I'm in for
it. All right. You can do it. This time the blank is first.
Okay.
So blank divided by 16.
Some number divided by 16. Okay.
Equals 240 divided by 8.
Okay. Some number divided by 16. So I'm thinking about how many 16s are in that number, whatever the unknown number is.
Okay.
Is equivalent to how many 8s are in 240. That's kind of what I'm thinking about.
I love that in so many ways.
Oh, okay. Well,
that's not how I thought about it. But how does that help you?
So there's some 8s in 240. But this time the group size is twice as big. So I need the amount to be twice as big to maintain the equivalence.
To maintain the equivalence.
Yeah.
Could you, I'm curious, could you do that? You did that with group size. Could you do it with the number in the group? Like if 8 was the number in the group.
How many 8s are in 240?
Is that? Yes.
How many 8s are in 240?
Then how does that help you reason?
Isn't that what I said? How many 8s are in 240?
Well, is that the number of groups or is that the number in the group?
How many 8s are in 240 is this?
That's the number in the group.
Yeah.
Okay. So you said if there's 8.
There's some 8s in 240, I think is what I said. Then I need to have that same number of 16s in some other amount.
Mm-hmm. And that would have to be
480.
Twice as big.
Yeah.
Yeah. So what I was wondering is if you thought about, I don't know if it's possible. If you thought about like there was 8 groups in 240.
I see what you're saying.
But now I've made
the group
16.
Size has doubled.
Now I've made 16. No, the number of groups. I've got 8 groups in 240. So if I make 16 groups, what total number would give me the same number of people in those groups? I don't know if I just said that right.
I feel like we're saying the same thing. I was thinking about how many 8s are in 240. So I need that same number of 16s in 480. And I think the opposite or the other way of thinking about that would be I have 8 of some size in 240 and I need the same amount, but now I'm thinking about the size of 16s.
Yep, that works for me. So what if I also thought about it as equivalent ratios? So if I could picture that as, I said the symbol divided by, but if I put sort of a blank divided by like over, and I'm just saying, so what it looks like on my paper, like out of 16, and then I had 240, not out of 8, then I can kind of think about equivalent ratios. And to get from the 8 to 16, I double, and to get from the 240, I would double the dividend.
Yeah.
I need the numerator.
I need to get myself to record division more in that way. That's a thing I'm going to work on.
All right.
Because
I like it.
I love that.
I like it. So another way that I'm thinking about it that I hadn't thought about till right now is what if I was thinking about dimension and area? So it's almost like I'm saying I've got a dimension of 16. I just drew like a side length of 16. And I don't know what the area of the rectangle is. And that has to have the same side length. The other missing side length has to be the same as if I had a side length of 8 and an area of 240.
And you can even consider that. I just sketched out what you were saying. You can even consider that without knowing the other dimension. I just have a kind of like a line or one dimension that's just kind of doesn't end.
Yeah.
And I have 8 and 240 and 16 and some amount. And I can tell that because the 8 doubles to the 16, then whatever the area is going to have to double as well.
It's going to have to double. Nice. It's almost like you take the 8 by whatever is 240, and then you literally like copy that rectangle and put it next to itself to get the 16 by double the area.
Yeah.
And it's all based on the fact that we have to keep that unknown dimension the same.
Yeah.
Yeah. Oh, that's interesting way to think of it.
It's a really nice routine for cementing equivalence.
Yeah, because the equivalence sign, the equal sign means equivalence. It doesn't mean do it. All too often we get students who see an equal sign and they're like, oh, now I must do the thing.
Yeah.
And whatever comes before it, they sort of do. So like, for example, that first problem, 15 times 18 equals 30 times what? They might say, no, it doesn't. Like 15 times 18 is not 30.
Yep.
And to which we want to say, no. Like the equal sign means equivalence. You've got to figure out what goes in that blank to make what's on this side of the equal sign equivalent to what's on the other side of the equal sign. And that can help sort of build this idea of what the equal sign means. I think there's another thing that this particular routine that we call relational thinking, I think there's another really nice thing that it can do, which is help sort of cement the equivalence strategies. So for each of the 4 major operations, there's a strategy that is based on equivalence. It's based on how can I find an equivalent problem that's easier to solve. So for example, if I was in addition, a give and take compensation strategy is, or I've got this nasty problem, kind of like the one you did, 3,999 plus 2,588. You're like, yuck. How could I solve that easier? Well, I'm just going to move the marble over and make it 4,000 plus 2,587. That's an easier equivalent problem. So you just solve the easier one. Similarly, for subtraction, the constant difference strategy, which we actually use to solve 6.1 minus 2.9. We used that. We thought about the difference between the two numbers and we shifted it up. We kept the distance constant to find an easier problem to solve. We're going to subtract 3 instead of subtracting 2.9. For multiplication, an equivalent strategy could be doubling and halving. So when you double in half, you're creating an equivalent problem, like 15 times 18 is equivalent to, well, double a little bit, double the 15 to 30. Then I've got to half the 18 to 9. I'm finding an equivalent problem that's easier to solve. And then for division, it's the equivalent ratio strategy. Can I turn that division problem into a ratio, find an equivalent ratio that's easier to solve, and then solve that problem? So this routine, relational thinking, can be really helpful to sort of cement those equivalent strategies. And we like that. So if you're interested to see where we've got these, Kim, tell us about where they can find relational thinking instructional routines. Examples.
Absolutely. You can go to mathisfigureoutable.com and check out the Learn Now section. If you go down to Learn Now, then you will find the Instructional Routines Hub that has all kinds of relational thinking. You can click on each one, find out what people have said about them on social media. You can also find the link in the show notes. That's bit.ly/instructroute, INSTRUCTROUT.
It's like instruct routine. But we didn't finish the word routine. Like, quit making fun of my Bitly link. It's fine. Hey, so Kim, lastly, before we end this episode, I just wanted to tell you, I was just having a conversation with a colleague of ours who said, whoa, those infographics that you guys created for the developing mathematical reasoning, those are amazing. Pam, how come you haven't talked about them more? And I'm like, well, how come you haven't noticed when we talk? I mean, great, let's talk about them some more. So I just want to make sure that if you haven't heard about them, if you haven't looked at them, y'all, you really need to check them out. They are amazing. Not only do they break down the domains of the development of mathematical reasoning to help you really get a sense of each of the domains, but we also have video of real kids doing that particular kind of problem using different levels of reasoning. So for example, you can see a student solving a multiplication problem using a counting strategy, using additive reasoning, and of course, using what we hope to get them to build them towards using multiplicative reasoning. So it can be very helpful for you to get a real sense and a feel for what we mean by these different domains of reasoning as we develop mathematical reasoning in our students. You can find those at on the website, mathisfigureoutable.com/blog. When you get to the blog, look for the Developing Mathematical Reasoning Part 4. We'll put all the links we mentioned today in the show notes, but if you want to find that blog, it's Part 4, Development of Mathematical Reasoning. Development of Mathematical Reasoning Part 4 in the blog under Learn Now on the website. So, if you want to learn more mathematics and refine your math teaching so that you and your students are mathematizing more and more, then join the Math is Figureoutable movement and help us spread the word that math is figure outable. Thank you for listening and making math more figure outable.
To learn even more, make sure you register for our free challenge at mathisfigureoutable.com/challenge. You are not going to want to miss the evenings of May 15th through 17th, starting at 7 p.m. Central.
Math teaching, go register now. That's mathisfigureoutable.com/challenge. Join us to make math more and more figure outable. And if you can't join live, register and we'll send you access to the recordings. We'll see you there.